Okay, so let's get started with Ricardo's second lecture on the standard model and quantum field theory.
Okay, good morning. So last time I spent a considerable amount of time, right, trying to convince you guys that the first step we should take when building these Lagrangians for particle physics is to worry about symmetries, right? And the main symmetry would be the symmetry under Lorentz transformation. So we did this classification of the fields according to how they transform under the Lorentz group, right? And now I want to show a few examples on what are the simplest Lagrangians you can build out of those fields, right? And give you a little taste of what happens when we quantize those theories. Mostly we will be building the classical Lagrangians, right? But by looking at the classical Lagrangians, and if you know a little bit on how the quantization works, you can guess what the quantum theory is just by looking at the Lagrangian, right? And that's the information. How to read Lagrangians is part of the information I want you guys to keep, right? So that's something you can learn to do, and even if you don't understand the fundamentals behind it, right, you can use it to just look at Lagrangians and know what you are talking about. So the first one, I'll show a little bit of this. Since I'm not proving stuff, I put some of that in the slides, right? So that's the simplest thing you can think of, right? So it's just the scalar field. Remember this symbol I'm using for the guy that under Lorentz transformations goes into itself. So phi prime of x prime is just phi of x, right? Does not transform at all. It's a scalar field, right? So I can put basically any term involving this guy there, and I know that the Lagrangian is Lorentz invariant. The only care I had to take here is about the derivative itself, right? So this is the derivative in x mu, right? So I had to contract with another derivative, otherwise it wouldn't be Lorentz invariant from the explicit dependence on the derivative, right? And I put a phi squared term there. Why this form, right? I could put a linear term in phi, I could put a phi cube, a phi fourth, right? The reason this is significant to us is because that's the one we know how to solve, right? That's the harmonic oscillator of quantum field theory, right? That's the one we know the exact solution for in 4 dimensions, right? So you can show this as an exercise for you. If you apply Euler-Lagrange equations here, just extremize this action, right? You write an action based on this field, extremize it. You see that the equation of motion for this classical field is this one, right? Which is a well-known equation, right? And then you solve that one, you get solutions which are exponentials, right, for some frequency, right? See, this is defined as the positive, that's important, right? This omega is defined as the positive square root of k squared and m squared. You have to go to momentum space to get this solution, right? And so the most general solution is this one, right? Where a and a dagger here are just coefficients, right? This is just a Fourier decomposition, right? No big deal here. You can check this is the solution. Just substitute there and do the derivatives. You'll see that this satisfies that equation, right? What happens when I quantize this thing, right? Then I will impose, I will get that pi of x and t, right, which is just this. Right? I define this other field. It will also involve a and a dagger, right? I just apply these derivatives here, right? And then I impose this commutation relation, right? As I said last time, this is quantizing the theory. I treat these two guys as operators, and I exchange the Poisson bracket by this commutator. But of course, I can go back to phi and pi, right? And derive now commutation relations for a and a dagger, right? I'm deciding to put a hat on these two guys, so they will carry the operator character of the field. Right? And it turns out that this relation is, if you exchange this K, right? Suppose I put this on a box. My universe is now a small box. This will quantize this momenta, right, inside the box. And this Dirac delta will become a Kronecker delta between momenta, right? So this is just a really extensive sum of harmonic oscillators, right? This is the commutation relation for a harmonic oscillator. Based on that, I can build a Fock space, which is the good basis for a not forced harmonic oscillator, right? And then these guys will act as creation and annihilation operators. You know the drill, right? You have seen this in quantum mechanics. If you keep applying the annihilation operator, eventually you can define a state where applying the annihilation operator gives you 0. You call that state the minimum energy state of your system. In quantum field theory, we call this the vacuum, right? Whatever state is the minimum energy of the system, it's called the vacuum. There's no particles there. And then this operator creates excitations on top of that, and you can define a whole tower, and that's the spectra of your theory, right? They are all eigenstates of these number operators. So the main point here is once you do that, right, you can write a lot of the other operators in your theory, which are written in terms of phi and pi, in terms of A and A dagger. Right? For instance, for that system, the Hamiltonian will look like that. The Hamiltonian operator can be written in terms of phi and pi, right? But then you expand both in terms of that solution, and you get this one. So this is the Hamiltonian operator. Before any tricks, right? It looks like that. Right? Why do I need tricks? Because of this, right? So if you look at this, again, you can always think of putting this guy in a box. This integral becomes a sum in momenta, right? The momenta becomes discrete inside the box. So I'm summing over many harmonic oscillators with different frequencies, right? For each k that is allowed in the box, I'll have a frequency determined by that parameter which I like to call mass, right? So the expression for omega was in the previous slide. If I can go back to it. So this is the expression for omega, right? So for each moment I have a different omega. The smallest one should be with momentum 0, right? Just the mass. But I have this thing, right, which is a sum over half, infinite sum of halves, right? And that's the infinite energy of the vacuum, right? Which we don't care as long as nobody turns on gravity. As I said, gravity, we don't want it around. And the way to go around that, right? Of course, you always have to define a minimum for the system, right? And you define the spectrum of your theory in relation to that minimum. The way to do that here, you define a normal ordered Hamiltonian, right, which gets rid of this half part, because this comes from, this was something like that before, right? I just commutated these two guys and got the half. If I say I will normal order, means I can bring this guy up front without using the commutator. That's normal ordering. Right? So I get rid of the half, so we can define an energy, right, operator, which will give you the energy of the system, just by this part. Where nk is just a number operator. It's just this guy, which counts the number of excitations with momentum k. Right? Just counts how many excitations I have with momentum k. right? Above the vacuum, above this vacuum, which is potentially, I don't know, has infinite energy. So it's the same problem with this is just the rest energy of a harmonic oscillator again, right? But now I have an infinite number of harmonic oscillators, so there's a lot of halves around. Turns out that you can define a lot of other operators, right? I define this pi, and it's kind of tempting to think this is the operator that will give me momentum, right? Because it's the canonical conjugate momenta to this variable. But in fact, it's not, right? What you have to do to find the momentum operator is the same that I did to find the Hamiltonian operator, right? I have to look at the symmetries of my theory, right? And use Nether's theorem. Who knows about Nether's theorem? Just as a curiosity. I'll talk about it a little bit, but the gist of it is you have symmetries under continuous transformations, you get conserved quantities, right? And invariance under time translation gives you a conserved quantity, which is energy. If you use that and use Nether's theorem, this is the operator. If I do the same for space translations, right? Translations in X, Y, and Z, the conserved quantity is momenta. So I can use that to find the operator, and it turns out that the operator looks like that, written in terms of A and A dagger, right? This is the momentum operator, because it is the conserved quantity under space translation. So this is the stress energy tensor, right? And the space components of the stress energy are the things conserved under spatial translation, right? And you can now write this guy in terms of A dagger, and it turns out that you get this. Ki, right? This is the X, Y, and Z component. So when I use I, it goes from 1 to 3. When I use mu and nu, it goes from 0 to 3. Right? So I is just the 3 space components. And again, the number of excitations. So you see, for this theory, things are really simple, right? I can diagonalize the Hamiltonian, the momenta, and the number operator at the same time. That means I have a basis of states where I'm counting these excitations. And every time I create an excitation, I will create an excitation that has a number 1, let's say, of excitations, but it comes together with energy omega k and momentum k. And this omega is defined as written there, k squared plus m squared. These are particles, right? Particles that satisfy the relation between momentum and energy detected by special relativity, right? They satisfy the dispersion relation, or the relativistic dispersion relation. This is actually what defines mass in these theories. There's no other definition of mass. Right? When you wonder what is mass in particle physics, this is it. Right? It's this number that relates how energy increases when I increase momentum. That's all. That's the only definition you have, because when you measure particles, the only thing you actually measure is how much energy they left in your detector and how much momentum they had, right? And then there's this number, which now I can interpret that parameter that I had in my Lagrangian, which could be just an A phi square, right? But it's already, since you know the answer, written in exactly the right way, right? I put an m squared over 2, and it turns out that I have an m here. If I just put an a, I would have something like a 4a here, and then 4 square root of a, in fact, and then I could rename that as a mass, right? But you start, and there's a few important things here, right, which confuse people a lot when they get renormalization in front of them, right? This identification, saying that that number in the Lagrangian over there is the mass of the particle of the theory, was an identification that I made for a free theory, for this theory in particular, right? That changes when you put interaction. So this mass is only a mass in this particular Lagrangian, right? It might get corrections from interactions, from clouds of virtual particles and all that mass, right? Mass with an E, right? So keep that in mind, right? But that's where the particle interpretation for these theories come from, right? You have these excitations, which are quantized, right? They come in packets, right? These packets have the right momentum and the right energy to satisfy a dispersion relation. And that's because this theory is too simple. That's basically all, right? If I had spin, and as I told you yesterday, right? If I was dealing with this field, each of these excitations would also carry half or minus half unities of momentum. So it would be a spin half particle. If there was a charge, how would I make these into a particle with charge? I just have to make this field a complex field. Then each of these excitations would carry each plus or minus integer unities of that charge. Right? So everything works out for the particle interpretation, right? And the messiest thing in quantum field theory is try to define states in your quantum theory that are asymptotically becoming these states of this theory, which is a free theory. I'll argue in a second why, right? And so you have to do a lot of groundwork to define a theory that has interactions, and in the same time, as particles move away from each other, they become single particle states and not a mass of interacting particles, which are very complicated states. Right? So another two examples I could give of that are these, right? Now for the spinor field and for the vector field. So up there you see the same thing, essentially. I have one term that has this derivative, right? Which gives me the kinetic part, right? Gives me the momentum, right? And I have another term which is essentially quadratic in the field, right? That gives me the mass. But now the normalization of the mass is different. If I would do the same I did here, I would get exactly the same Hamiltonian. But now for creation of these guys, with one difference, this is a complex field. So I would have two types of A's and A daggers. I would have some B and B dagger. One of them creates particles, the other one creates and annihilates antiparticles. So now I have two different excitations of the same field, because it is complex, right? Complex field, you need two numbers to specify it. The real part, the complex part, the modulus and the phase, you name it, right? So you have two kinds of excitation for that field. And this is what you get for the vector, right? Now you could screen at me and say, well, this is not the simplest thing, right? You could just write something like that, right? Even the m square is not obvious, right? But you could write something like that. I could. In principle, I could, right? I'm not writing it because I have a prejudice about gauge bosons with masses, and you'll see why in a few lectures, right? But this is basically the Lagrangian for all the fermions you know, right? They obey something like that with different masses, okay? And this is the Lagrangian for the electromagnetism, right? If you apply Euler-Lagrange equations to these guys, right, this is the vector potential, right? And you get all Maxwell equations from here in the vacuum, right? I mean the vacuum here. Go ahead.
When you have in particle physics, you have like the baryonic number, the atomic number, and you count the antiparticles as negative. Does this number operator function in the same way? Or
No. No, the short answer is no. The way all these other numbers work, baryon number, lepton number, they are really charges. So you have the number of particles is always positive, right? This number operator is always positive. But say if you would calculate the baryonic number, you would have some operator, right? This is the total baryonic number. And it would be of the form of course, you have these integrals and whatnot. But in terms of these A's and A daggers, it would look like that, with a minus here. So when this number of particle type A increases, the baryonic number increases. When the number of particle type B increases, which is the antiparticle of particle A, then the baryonic number decreases. And if the total number is the same, the charge is 0. Right? This is true for all charges. This is true for electric charge, for baryonic number, for leptonic number. We'll see about hypercharge pretty soon. It's the same. Right? So every time you have particles and antiparticles, the conserved charges in your theory will behave like that. Right? You have two number operators because you have two kinds of excitation. One of them with charge plus and the other one with charge minus. Right? And we'll see these arises from a symmetry, which I'll talk about in 10 minutes. Right? So these are, what do all these theories have in common? If you look at there's always, they are always quadratic in the field, right? If you take all terms here, you do the distributive here, you always find 2 powers of A. Here, there's always 2 powers of psi, and in the one I had before, there were 2 powers of phi. This is not working well, right? 2 powers of phi, 2 powers of phi. That's why the reason of this is that this is the harmonic oscillator, right? So you had a square. If you were quantizing this into path integral, this would translate to a Gaussian integral. This is the kind of things we know how to do. Probably the only thing physicists know how to do, right? Gaussian integrals and harmonic oscillators. So these theories are the ones we call free theories, right? And the reason is that having only 2 powers of the field, the only thing that can appear is something like A dagger, A dagger, A, or A dagger, right? Most of these make no sense from the point of view of energy conservation, right? If I start with a vacuum and create 2 particles, right? This does not conserve energy. Same thing here, right? If I start from a state with 2 particles and apply this operator, there's nothing. It disappears. Time is flowing to the right here, right? But these two make sense, right? I can annihilate an incoming particle and create an outgoing one, but nothing is really happening. The particle is just moving around, right? This one is 0 in the vacuum. Right? Actually, it's the opposite. This is annihilation. So this is 0, because just try to annihilate the vacuum. This one is the one I'm talking about. It's just propagating. So these theories are free because the number operator commutes with the Hamiltonian. So as the system evolves in time, no particles will get created. In fact, you don't even move from one Fock state to the next or below. You just keep them. The state just evolves in time without changing. Right? So in order to have interactions, right, for something to happen, you need to put terms that involve more than 2 powers of the fields. Otherwise, you get nothing, right? So these are the free theories, and here are a bunch of examples of interactions. So suppose I take that theory I started with, right? And I add now this lambda phi 4 interaction, which is the toy model, the favorite toy model of quantum field theory courses everywhere. Now I'm talking about this. And usually we normalize with a 4 factorial here, but that's not important for you, right? This is now interacting theory. Why? Because now I have all these possibilities, right? When I expand my Hamiltonian, right, it will involve this 4th power of the field, and you get this A, dagger, all these options, which we indicate in diagrams like that if I keep time flowing from the left to the right, right? But that's not what we do. We just indicate. Now I'm making a very shoddy introduction to Feynman diagrams, right? We just indicate it like that, right? I'm saying that in this theory, and remember, this is a local theory. So these fields are all acting on the same point, right? They all depend only on one space-time coordinate, right? So this 4A A dagger operators will act on the same point X, right? And now I'm saying when I draw a diagram like that for my theory, I say, well, I can put the legs in the past or the future any way I want. I can do all the combinations, but that tells me that I have this possibility of 4 fields interacting in a point. Right? So now this theory has this possibility of starting with 2 particles with momentum K1, K2. Right? They are annihilated by a K1 and a K2 acting on that point. And then an A dagger of K3 and an A dagger of K4 creates 2 different particles at the end. I mean, it's the same particle because this field only has 1 particle, but they have exchanged momentum. Right? If they exchanged momenta, they have scattered. And I can calculate the probability for that scattering to happen and compare with experiment. Right? So now this interaction creates the possibility for interaction. Right? So essentially, the game we're playing here is trying to write the free part of the theory will be always the same. I'll just have many copies, if I can, of these things, right? For each fermion, I'll have just a copy of this block and add many of them, right? For each scalar in my theory, I'll have a block like that. And if it is a massless scalar or massless fermion, all I have to do is write the same thing with mass 0, right? Just eliminate that term. And for each gauge boson, for spin 1 particle, right? For each spin 1 particle, I put a block like that. I'm not saying how I will put mass for these guys, because mass for gauge bosons will be complicated. We'll get there, right? Well, there's one thing I didn't say is that the overall probability will be 0 unless momentum is conserved. So in this one, I have K1 plus K2 needs to be K3 plus K4. So K1 does not need to be the same as K3. It could be, but it does not need to be. Here, K1 and K2 must be the same, right? And this particle has no other property, in this case of this scalar field, has no other property than momentum. So if K1 is equal to K2, it's the same particle. There's no way of you knowing that anything happened. No, in this case, I'm saying I started with a state of K1. I acted with an operator that annihilates K1, creates K2, and I end up with K2. Right? In fact, it was that one. I keep messing up. Right? So now the game is, I can write many blocks of these, but I'm just putting 3 particles there. And I'll use the symmetries, right? Other symmetries, to fix the interactions. Right? And that thing that is on front of the interaction is very important. That lambda that is there, right? Because that measures the strength of the interaction, right? It's obvious that if I take lambda to 0, I go back to the free theory. There's no interaction anymore, right? And that's the trick we use, right? Because we don't know how to solve this. This is another oscillator. It's not the harmonic anymore, right? We don't know how to solve this. We don't know how to do an integral. I put that on top of a exponential. It's not a Gaussian anymore. I don't know how to solve this, right? Nobody knows. But I can do is that if lambda is small in some sense, then I can do this perturbatively. I can start with the free theory and put small corrections due to the interactions, right? So we name these guys coupling constants, right? And they are the ones that control the strength of the interaction. It's just the number that appears in front of the interaction term, right? And to give you a few examples of interactions, right? Here are many, right? So lambda phi 4 is the one in the middle, in the top there, the one I just mentioned, right? But this is how QED looks, right? It's just an interaction between 2 fermions and a gauge boson, right? if I write a free theory for electrons, right, just the term I just showed you, plus F mu, which gives me Maxwell equations, plus this one piece in the Lagrangian, just these 3 building blocks, that's QED. That's the whole story for QED, right? Probably the most successful theory ever made in terms of comparison with experiment. Right? This is very important too. This is the first interaction that people use to model the interaction between protons and neutrons and between themselves. That is a strong nuclear force, right? Phi here would be the pion. Once you put that in, you allow, if the fermion here is a proton, right? What you are allowing is for a proton to emit a pion, right? Which then can be absorbed by another proton. So here is where the Feynman diagrams start to appear, right? And they are a perturbative thing, right? This is a consequence of the perturbative thing, right? Because what is entering here is that Y there is the coupling. It's called a Yukawa coupling for this kind of interaction, right? And it is entering here twice, right? This diagram would mean nothing at all. It wouldn't be useful at all if I had to worry about this one, and then this one, and then this one, and then that one, right? And the only reason I can stop at the first one and get some meaningful result is that Y is small and I'm increasing a power series in Y here, the more interactions I put, right? So you can do the first thing, which is calculate this, and everything else are corrections, which you can actually calculate, right? Another beautiful thing is that you can prove from this diagram alone the Yukawa potential, right? You can take the non-relativistic limit of these theories and prove get the Yukawa potential. Right? And this one is one of the complicated ones. This is just one of the many interactions of QCD. It's just one, there are others, right? This one is what you get from F mu, but now there's a color index too, right? If the field here is the gluon, not the photon. Then there's this gluon-gluon interaction with all these factors. These are the structure constants for the Lie group, right? I think Nathan mentioned that in the question session yesterday. These are the same. These are the structure constants, right? And that's why gluons interact with gluons, right? Differently from photons, right? So you cannot build lightsabers out of photons, but gluons maybe, right? They scatter against each other, right? So now we want to use those ideas to start getting towards these interactions, right? But first I have to talk a little bit more of symmetry, right? So in Nathan's course, you're focusing mainly on symmetries which are transformations in space-time, right? You're doing this big extension of the Poincare group, right? Here we'll focus more in another type of symmetry, but there's still one part of the Lorentz group which is important. Why is this? I think I skipped more than one slide, or did I forget something? Oh no, before I go to the next slide, let me do something on the blackboard. So there's one more part of the Lorentz group we need to take a look at, which is the discrete part, right? Which we didn't talk about yet. But you can define the Lorentz group by the group of transformations that leave this object invariant, right? And of course, all the rotations and boosts do that, right? So it's the same as square, right? All the rotations and boosts do that, but there's 3 more symmetries that also do that, and which are discrete. And one of them will matter for us a lot. So there's charge conjugation. As I said, in the case where fields are complex, and I show an example right here, right? Both on this diagram and this diagram, I have these arrows on the lines, which are indicating for me the flow of the conserved charge he asked about. Because every time you have a complex field, you have some kind of conserved quantity, right? And this is a particle. When the arrow is flowing towards the future, remember time for me is flowing to the right, they are particles, and when the arrow is pointing towards the past, they are antiparticles. So the total charge was 0 at the start and 0 at the end. Same here, right? And I could draw diagrams like this, right? You see that the charge was positive at the start, positive at the end. So it was 2 here and 2 at the end. It's always conserved, right? So this symmetry, it exchanges particles for antiparticles. So I can define an operator. I won't do it here, right? But you can define an operator and get the properties, how it acts on states created by these theories, etc. Right? That's one of the symmetries. The other one, which is the important, very important for the construction of the standard model, is this one. It's called the parity transformation. Right? What you do is you invert all the axes of space, not time. You leave time untouched, and you exchange x by minus x, y by minus y, z by minus z. Of course, this leaves these untouched, like this one. This one is not, you're not even doing anything with space-time, right? But if you think a little bit about it, you see that when you do this inversion, the parity transformation, right? What I'm doing is this. I start with my coordinates. In fact, I started with them in the wrong way. Right? And then you reflect this, right? You exchange every coordinate. So x now will be going there, y will be going down, z is going backwards, right? And have this new system of reference. But you can rotate that, right? To make y and z coincide with this y and z here, right? And that will give you, this is the parity transformation. That will give you this thing with x pointing over there now. Right? So really the transformation is the same as inverting one of the coordinates without touching the other two. And that's exactly what happens in a mirror. Right? When you're looking in a mirror, you're not changing anything in the direction which is parallel to the mirror. But as you move to the mirror, the image moves towards you. So you're exchanging that direction. And that changes something we call chirality, right? Which is the vector product between these three guys. It inverted, right? Now, if the right-hand rule here becomes the left-hand rule here, and vice versa. So really, what parity is doing is changing chirality, and that's why it's important for the standard model, right? You wouldn't expect these to be violated in nature, but nature doesn't care about our expectations, right? It's really violated, right? It's violated everywhere, in biology a lot, right? You have a lot of these molecules which have some right-hand rule. And if you invert that molecule, then no other enzyme or bacteria can deal with that. But that's historical, right? Just chains that happens that at some point in evolution, one of the kind of molecules become dominant, the other one doesn't, and every living being adapted to the version that was around. Right? Because the interaction behind that was just electromagnetism, and that respects chirality. You wouldn't expect, though, for fundamental interactions to care about particles being right-handed or left-handed. You wouldn't even expect particles to be right-handed or left-handed if they have no size, right? But they do. They do have chirality, right? It's the same as angular momentum, right? You're already used to things without size having spin. So this is not that different from before, right? You just have something that has no size, but has this intrinsic chirality. And we'll see that some of the interactions of the standard model violate this a lot. And the final one is the same, but instead of inverting these 3 coordinates, I just invert time, right? That also leaves this invariant, right? And there's a theorem, which is called the CPT theorem, that says that every quantum field theory, which is local and unitary, also has CPT, is invariant under these 3 transformations at the same time. Have to do the 3 of them. But you can violate them individually and compensate by one violation by violating the other. And the standard model violates everything, right? It only does not violate CPT as a whole, right? And we'll see about that. Now, that is all well and good, and it finishes what I care about, the space-time transformations. Right? Now I want to talk about a different kind of symmetry that your theory can have, right? Which is what we call internal symmetries. Oh, go ahead. It forms a group with the Lorentz transformation, but they are discrete. So this is not when you include these guys, there's no more generators. They are not a Lie group anymore.
So they will not be crossing other groups like symmetry of the standard model.
Well, all these symmetries, they have to be satisfied at the same time. But what you get in the end is a direct product of all the operators that act with this on the states, right? So in the end, they are independent. So symmetries that belong to a different, let's say, group, they commute between themselves. So you have these direct products of groups. Right? We'll see that in practice pretty soon with the internal ones.
Yeah, for the conservation of these quantities that you're describing, we have all the charge of the operators, but we don't have a time of it.
No, be careful. These are discrete symmetries. So they are not subject to Nether's theorem now, right? So you have to be careful. So Nether's theorem applies to continuous transformations, not discrete ones. So these guys, what I'm talking about, the conserved quantity for for time is due to time translation, this transformation. You just translate your system in time. This leads to energy conservation. Translation in momentum, right, leads to in fact, translation in position leads to momentum conservation, right? So these are all continuous symmetries. These ones are not. So now, the internal symmetries. What is an internal symmetry, right? You can think of many examples, right? So, for instance, everyone here knows what an electron is. Maybe some of you know what a muon is, right? But a muon is like a heavy cousin of the electron. It's equal to the electron in every respect, with the exception that it has a much bigger mass, like 200 times bigger. Right? And suppose I map very, very high energies. So I can disregard the mass. I can treat both the electron and the muon as massless. Right? In that condition, I have a symmetry where I can define a state which is an electron-muon state. Right? Because I cannot differentiate between them anymore. And I have plenty of energy to create muons and create electrons and disappear, so I could have even coherent states between those guys if I can ignore their masses. Right? So symmetries like that appear everywhere in the standard models. So one famous case is the color of quarks, right? A quark can be a red quark, a blue quark, a green quark, right? This name mean nothing, just tell me that there are 3 different quantum states that I decided to call color, right? Which the quark can have. And this is a perfect symmetry of nature. There's no interaction that can tell you if the quark was red, blue, or green. So it's a perfect symmetry. And it is an internal symmetry. I'm just saying, if I go to my Lagrangian and exchange all red quarks by blue quarks, nothing should change, because this is not possible to observe. Right? But I'm doing nothing with space-time. It's a transformation of the field alone. Right? This is what we call the internal symmetries. And the simplest one, right, is the one that appears when I make that scalar field a complex one. So let's say I take this Lagrangian, right? Or something very similar to that. And now I make this, right? I say, instead of considering a scalar field, I will consider a complex scalar field. So now my field can be written in this way, where both phi 1 and phi 2 are real. So now I have 2 degrees of freedom. For each point in space, I'm assigning 2 numbers instead of just 1. Right? In particular, I can demand that my theory is invariant under a unitary transformation that changes the phase of this complex field. Right? So I can write that unitary transformation like that, right? And say, well, I want my Lagrangian to be invariant for that because this phase, this complex phase, shouldn't be unobservable, right? Then the Lagrangian is not good anymore, right? This one is not good anymore, because this will be proportional to twice that phase, etc. Right? I had to change my Lagrangian. So let's write the new one, right? Just to. So my Lagrangian now will have to involve phi and phi star, right? The complex conjugate if I want it to be invariant. In particular, we can change these normalizations to get the right spectra for particles, right? But this is invariant now, because I'm assuming theta here, this phase, is independent of position, right? That's equivalent to saying that I'm defining the group of these transformations is called U1, right? And it is a global version of it. That means I'm making the same transformation all over space-time with the same theta. Right? It does not depend on position. That's why I call it global. Right? This is also good, right? Notice that the factor of 2 went away. And that's because I know that when I quantize, write everything in terms of A and A daggers, if I don't put a factor of 2 here, this will be the mass. But I have to do the whole calculation to see that. Okay? Now, a term like that one would be forbidden, right? It's not invariant under this, right? So anything that had a different number of phi's and phi stars, right? Like this one, or any term that has odd number of phi's will have a different number of phi's and phi stars, and that's not allowed. I'm forbidding a lot of the things I could have here, right? And the interaction can be anything of this form, right? The only constraint now being something I mentioned last time, which is renormalizability, right? If I make this power too big, then I'm putting interactions that only matter when I'm really close to the breakdown of the theory. But if I'm far away from there, all these interactions go to 0, right? And then the only one really allowed here is a factor of 2. Right? It's the phi 4 again, but instead of having phi to the 4th, I have phi star, phi star, phi. Right? So that's one theory that I could have. Now suppose I want to be more ambitious, right? This is the old way of getting to these theories, but it's the simplest way. And now I want my theory to be invariant, even if I'm changing the phase of the field differently in different points of space-time. In fact, it should be minus here. I'm not being very careful. This is the potential, right? If you write this in terms of kinetic energy and potential, this is T minus V, right? And I want V to be positive so it has a minimum, right? So this should be minus everywhere. But I'm not being careful, I'm just worrying about the operators. And the factors of 2 are just normalizations. I'm getting the right normalization. This should have a n over 2 factorial here, something like that. Now, if I want to make theta, right, now I want this theory to be invariant under a local U1. I'm making different changes of phases everywhere, right? Now, theta is a function of space-time. Yeah. Now you can see that nothing changes here, right? Nothing changes here, but this one becomes tricky, right? Because this thing does not pass over does not commute with the derivative. If you try to do that, you get extra terms, right? And these extra terms have to be compensated. So this Lagrangian is not good yet. And I cannot just eliminate this guy, because then I eliminate momentum from my theory, right? I don't have anything that propagates. I need a term with derivatives, right? So I can do something which is put another field to compensate for the extra part that comes from here when I try to do that, right? And that is the so-called gauge field, right? And it has to transform. When I do this transformation on this guy has to transform in a very particular way to conceal the extra terms that come from the derivative acting on this exponential. Right? And the way it has to go is this way. This constant in front is arbitrary, right? But it sets the coupling constant for the interaction that will come out of here. Right? So this is the convention we use. So if I have now this field transforming in this way, and that one transforming in that way, now I can define, again, a covariant derivative, right? We already saw a covariant derivative for the Lorentz transformation, in the case of fermions, right? Now I can define a covariant derivative for this guy, right? So I can define a new derivative, which we call it like that, right? And which is given by this. And then you do the U1 transformation. These new derivative transform covariantly, right? So it transforms in the same way as the field. So now if I go back to my Lagrangian and replace this and this, right? This becomes trivially invariant because this guy will get an exponential of I theta, exponential of minus I theta, and then that's invariant, right? So I have to define these. So in fact, exercise 3 is to show this. Right? Did I tell you about exercise 2? I hope so. Otherwise, I'll go over it at the end and remember the exercises. But prove this. It's very easy, right? Just have to substitute these and show it's invariant, right? Show the derivative transforms like that. Another thing is that now I'm putting a new field in my theory, right? And if this field will have excitations too, right? If these excitations are to be particles, they also need a kinetic term for this guy, right? And this kinetic term now has to satisfy not only the Lorentz invariance, it also has to satisfy this new symmetry, right? Which is the gauge symmetry. So this is U1 local or the gauge symmetry U1, right? And what is the kinetic term that does that, right? I have to add to that Lagrangian a new part. Right, so I can rewrite that Lagrangian in this way. So essentially what I have is del mu phi modulus square, right, over there, the first term. The second one is just m square phi star phi. And then I can put this one, which is the kinetic term for photons. Right? What I cannot put is this. Right? Because this is not invariant under this transformation. So that's why I was not putting masses for these guys from the start. Right? Bosons that transform as gauge bosons cannot have mass, at least not in this very trivial way. Right? We'll have to put a lot of work to actually get mass for these guys. We know in the standard model there's the W's and the Z's, right? They have mass. So the story is more complicated there. So just to give you the Lagrangian, right? This is QED. Of course, I remove this just because I want that interaction that is fixed by the symmetry. Just a second, let me show the whole thing, and I'll go to questions. So that's the Lagrangian, right? If I take this part here, notice there's this covariant derivative here, right? Which is this. And I just make all the products here and separate the quadratic part from the part that involves more than 2 powers of the fields. Right? Then I end up with just the kinetic term for the scalar here and these 3 pieces. And you see now that the symmetry is telling me how these guys interact. In particular, the same coupling constant applies to both interactions. This is called scalar QED. It's how a charged scalar particle would interact with a photon. Think of pions, the pi plus, pi minus, right? Of course, they have the wrong parity, but there are other examples, right? There was a question there before. Who was it? Yeah, go ahead. The common one, right?
Just repeat the question for people.
Oh, repeat the question. He's asking about these derivatives inside here, if they should be the covariant or the normal derivatives. And they are the normal ones because this field that is in there is not transforming as the same as this guy, right? So if you check, and that's exercise 4, in fact, thank you for reminding me. If you put that transformation in there, you see that that term is invariant under F min u. F min u is already invariant under gauge transformation with normal derivatives. So you can check that explicitly, that this guy is gauge invariant. And that's why we first found gauge invariance in electromagnetism, right? It was there from the start. Right? So there was another question here. Because if you just substitute this there, right, you transform both A mu's like that, you won't get the same Lagrangian. And my main demand here is that the Lagrangian be invariant under this transformation. It violates gauge symmetry. Right? So it's forbidden by gauge symmetry. There are many ways you can say that, right? So, question. This one? No, it makes no sense to change the derivative of the field unless the field is also charged under the interaction that is appearing, right? But if you put it there, what you're saying is that you have del mu. If you defined a covariant derivative for A that transforms in the same way A transforms, it wouldn't even be this one. This is not a covariant derivative for A. Right? So it makes no sense to just apply this to A. You could, in principle, define one, but in this case, it's already the normal derivative. It's already covariant. Right? That's the point. So one important point that I have to mention is that this is kind of the old way of doing this. This is the historical way, it's the easiest way. But it kind of promotes this to an axiom of your theory. I'm demanding that it is a gauge invariant as a first principle, right? That is not how we think these theories nowadays anymore, right? It just so happens that if you want a particle with spin 1 in your theory, the only consistent theories that you can write that are explicitly Lorentz invariant are these ones. So you're putting these extra degrees of freedom in your theory, right? Exchanging E and B for A, right? As a way to get a theory that makes sense and you can prove renormalizability and all. Right? So gauge invariance is not seen as a fundamental thing anymore. Right? But it's very easy to see how it appears in this way. Right? To show it in the other way, it would be more complicated. Right? So that's just a comment that will confuse more than enlighten, but you should know. Now, what we will do with these, right? We could do the same for a fermion, by the way, right? Instead of using a scalar there, I could have used the fermion. The story is very similar. I just take the fermionic field and say I'll transform like that. So it's a U1 transformation, and it is local because it depends on X, right? Again, I need to define a covariant derivative. Is the same one I have there. Is this same covariant derivative, right? I also have to introduce a mu, but now I get only this interaction, right? And this is the Lagrangian for QED with just one fermion. Say the theory of electrons and photons. That's it, right? Nothing else. So, and it respects parity. There's no violations of C, P, T, nothing, right? It respects everything. And since we spent a good 1,000 years or more only dealing with this interaction, we started to believe that parity was a good symmetry of nature, time inversion, everything, because that's the theory we feel on a daily basis. Right? Gravity also respects all of this. Okay, so now this is a simple phase transformation, right? I'm just changing this phase of the field, but it could be more complicated. As I said, one of the main reasons we care about internal symmetries is that sometimes different particles under some interactions are indistinguishable by other interactions. One famous example is the nucleon, right? You could ignore easily the difference between a proton and a neutron inside a nucleus, right? Because the strong interaction is so strong that you can ignore electromagnetism, so the charge does not matter. And then the masses are really similar too, right? So you could, in principle, define a particle which I call nucleon, and it has two states. The up state I call a proton, the down state I call a nucleon, a neutron, right? So you have this index now, right, here, that goes from 1 to 2, and this is just like spin. In fact, you can build a whole theory. People call this isospin, because it's the same as spin, right? And these guys transform, right, under a SU2 group, which is the one that you have used all your life without knowing for spin, right? And it is a global one, right? So that the nucleon goes into a n prime, which is an exponential of some I. Alpha here plays the same role of this theta, right? It's just a number. Global one, it does not depend on position. But now this symmetry has 3 directions, abstract directions in which I can rotate these two guys, which are generated by the Pauli matrices, right? So I need 3 numbers. To specify a transformation, I need 3 numbers. You can think of that. Every time you get confused by this, remember, usually we put a factor 2 here, right? Remember 3D rotations. Another group, SO3, it's very similar to SU2, right? If I want to specify a rotation in 3D space, I need to specify 3 angles, right? That's the same here. Those are the 3 angles of SU2, right? And if you look at the indexes here, I have two sets of indexes, right? This A here, let me find another color. So this A here is going from 1 to 3 because it's running over the 3 generators of this group, SU2, which are the, you can choose a representation where these generators are the Pauli matrices. But you also have this index that goes from 1 to 2, and it's here, right? This is a 2 by 2 matrix, right? A Pauli matrix, which is contracted with the index B here. So every time I do this transformation, I'm mixing proton and neutron states, and I'm getting these mixed states of neutrons and protons. And I'm saying if I demand that my theory does not care if things are protons or neutrons, I can write a Lagrangian for that, right? And then you have to introduce pions as, you can also put pions here, right, and get a UCAL interaction between the proton and the pion. That's the one I showed at the start, and that's, to first approximation, a good description of nuclear strong interactions, right? Another famous one, now just to mention a local one, is what quarks have, right? So you could write any quark as a state that can have 3 different quantum numbers, right? 3 different states, which we call R, G, and B, right? Just as an analogy to color, right? And this, so that this is a thing that has an index now that goes from 1 to 3. And it transforms under, this is the fundamental representation of SU3 color, we call it, right? And it is a local one. So in this case, the quarks will transform like that. Again, I have these angles, right? So there is an index A here. But now there's 8 directions. In order to conclude that, you have to understand SU3, right? But SU3 has 8 generators, which are what we call the Gell-Mann matrices, which I will indicate like that. And then you have QR, Q, R, G, B here, right? So these Gell-Mann matrices, they have these index that go from 1 to 3. And it's contracted with the same index here, right? So the Gell-Mann matrices are 3 by 3 matrices that are in the fundamental representation generate the SU3 group. I think I have the explicit. These are the Gell-Mann matrices, one representation for them. You see they are kind of an extension of SU2, right? The 3 first ones are very similar to Pauli matrices, and that's not by chance, right? So when you demand that this is a local transformation, which in the quarks, the case of the quarks, it is, right? Then you get gluons. You have the same way I had to introduce the photon here, you have to introduce a gauge boson there, right? And that gauge boson, again, the same thing. I'll have to write a covariant derivative for this guy. But now the covariant derivative has to involve the generators, because you see, when I make this transformation on the Lagrangian, the derivative that acts here will take down these generators with it, right? So the covariant derivative has to involve these generators too. All the indexes have to be contracted here. So instead of having just one gauge boson, I'll have a gauge boson for each generator. So in the case of gluons, I have 8 gluons. They are all indistinguishable. That's why you don't usually hear there are 8 gauge gluons. You just say that's a gluon that has 8 states. It transforms in the adjoint representation of this group. So I think Nathan is looking me with an angry face, so I should stop here. I'll talk a little bit more on how this guy transformed next time, and we can go to questions. There's one there. Sorry, this one I didn't get a gauge boson. That's what you're saying? Because I'm assuming the symmetry is global, right? And that decision is phenomenological, right? So quarks, at first, the reason we postulated colors for quarks is essentially because of Pauli exclusion principle, right? By looking at hadron physics, we found a particle called delta plus plus that demanded that you had 3 quarks. The spin of this guy is 3 halves. So all the 3 quarks should have the same spin pointing up. And then some analysis of the angular momentum of this guy showed that these were all in the fundamental state, S wave. And then you had a problem, right? You had 3 fermions at same ground state. And the way people postulated said, well, they might have a charge, right? If there's a quantum number that has 3 different states, I could just say this is R, G, B quarks, right? And that's fine. That alone could be explained by a global transformation, right? Just say you have 3 states, you have this color charge here, and that's all. But then people are also trying to solve why these quarks were bound inside a proton, right? For that you need an interaction. And someone said, well, maybe that's a local symmetry, and you have gluons, and then people calculated the theory that arose from that, and it worked out. So these decisions of what theories I will make global or local are really phenomenological, right? You're just trying to describe what you see, right? So there are many local symmetries in the standard model. We focus on those because they're fixing the Lagrangian very strictly. But there are also many global symmetries. He talked about 2 already, right? Baryon number and lepton number. Those are coming from global symmetries, right? And this one is a global one, so you don't need a gauge, right? There's another one here.
What is the physical interpretation of the isospin and of the quark vector in those different phases? Like, what's the physical meaning of that?
Well, the moment you choose a representation, right? I choose to put the proton and the neutron together, right? That's the fundamental of SU2. I can also worry or wonder what would happen if in the same theory, I also have a scalar that has 3 states. This is like a spin 1 particle. But instead of spin 1, it's isospin 1. That's the adjoint of SU2. Right? That allows me to write a particular Lagrangian. I write it, and there will be some interactions there. But I could say, well, there could be a world where this is actually in the fundamental. Nothing wrong about that. I can postulate that. It will lead to a different Lagrangian with different interactions. What decides is the experiment in the end. You have to compare with the experiment. This one works. This one is not the one our universe chooses to be in. Right? They are all, from the point of view of symmetry, they both could be. Right? But the choice of how I organize these. So I decided that there were 3 quark colors. That's a model. Right? I could think of another model where I have a fermion with 8 colors. That would be a fermion in the adjoint of SU3. Right? That one would have to be a Majorana fermion. It's more complicated, but you could build a model around that. Right? And the reason we use the ones I'm talking about is because they are the ones that were realized in nature. What?
I understand that when you have that vector, you have like 1 proton. But when you take it to another basis and pass it to the matrix, and then I don't know, maybe you end up like 1 divided by square root of 2 minus.
No, yeah, that could happen, right? If you have these operators in your Hamiltonian, that means that time evolution could turn a proton into a neutron or even a mixed state proton-neutron, right? No, not here. Here's just a transformation. But if these generators show up in the Hamiltonian, and they will, right? Then the Hamiltonian can turn protons into neutrons. And it actually happens. What happens is, in nuclear physics, you could start with a proton state. And instead of emitting a neutral pion, so this is a proton, it emits a pi plus. By charge conservation alone, right, this cannot be a proton. So protons become neutrons as they emit pions and absorb pions. And neutrons become protons. And of course, if you allow these guys to be closed, very close together and not move away from each other, you could have coherent states which are protons turning into neutrons and neutrons into protons constantly, right? And that's a state that's not pure proton nor pure neutron. That's possible. Right? The total number of proton plus neutrons needs to be conserved. Right? Yeah, because that's the total charge of the nucleus.
Because I was thinking like some people have like I'm here, see a proton, and somebody's here and see, well, actually it's a neutron.
No, but that would be true if I was talking about a transformation of space-time. Right? You're still thinking in terms of rotations in space-time, like a moving observer. No, that's not. That's just a transformation of the form of the fields. Right? That's an internal symmetry. It has nothing to do with space-time. Right? But it is possible to build a coherent state of these two guys. What breaks that is electromagnetism. You have to disregard. This is an approximate symmetry. Right? This is approximate because electromagnetism differentiates proton and neutron. But this one is exact. So a quark could be in coherent states that is neither red, green, or blue, but is a mixed thing of those three. Right? Because there's nothing in nature that breaks this one. That we know of, right? Sorry, I didn't understand the question.
I'm saying that QR, QG, and QB in the cube state are spinors.
Yeah. These are, beside having this number that goes from R, G, and B, there's also, each of these guys is a fermionic field. So it's a spinor with 4 components in spinor space. Yes, the same. These are also fermions with spin half. Yeah. So this is another index. At some point, you start putting a lot of indexes in this guy, right? So you could have one that goes from 1 to 4, in which Dirac matrices act, right? That's the spinor index. Now I'm putting another one, color. Pretty soon I'll put another one for SU2, right? So these fields are multi-component things. But the important thing is that this matrix is only acting on this index. The Gell-Mann one that acts on that one, right, is acting on a different index. So this is a direct product of these two transformations, as I was answering someone earlier today. Right? In the end, you have many different generators acting on these guys, but they commute with each other. Each group is direct. The total group is a direct product. So otherwise, it could get very complicated, right? No, a lot changes. I can give you a few examples, right? So one of the things we'll worry about a lot is parity, right? Is this chirality of fermions, right? In 4 dimensions, that's fine. In 5 dimensions, you cannot define chirality. So it would be very different because you don't have the gamma 5 matrix, essentially. This gamma 5 matrix is something apart in 4 dimensions. It anti-commutes with every other Dirac matrix. You don't have one that does that in 5 dimensions. This gamma 5 becomes part of the Clifford algebra, right? So you cannot define parity in 5 dimensions. Then in 6 dimensions, you can define parity again, but the Dirac matrices are different size. So spinors have more degree of freedom. So it changes a lot if you go away from 4 dimensions. I'm not a specialist in working away from 4 dimensions, but everything changes. It becomes very different. Lower dimensions, again, you have also simplification. So if you go to 1 dimension, then there's no spinors anymore, right? Usually, the theories tend to become simpler in lower dimensions because the integrals start to converge. You don't need, there's no, people worry about infinities a lot. You shouldn't worry too much about infinities, but it's true that in lower dimensions, these theories, they start to converge and you have, but a lot changes, a lot changes. In 3 dimensions, again, you have this problem with the chirality, for instance. Yeah. There's another one here.
Do the Lagrangians we've seen today give place to 3 theories?
No, the free ones are the ones I shown at the start, right? Let me go back. This is actually here. So these are free theories, right? Because they only involve quadratic terms on the fields. So this is the free part for spin 1, the free part for a spin half, right? Already in the case of the spin 1, I'm assuming it's a gauge boson. That's why I didn't put a mass, right? Because of this. This is forbidden. And this is the free one for a real scalar. And that's the free one for a complex scalar on the blackboard. The moment I put something that is not quadratic on the fields, so 3 or more fields, then I get interactions. So all these theories I wrote here, right? In principle, I'll put interactions to that. But I always have to treat these interactions perturbatively because I don't know the exact solutions for the interacting theories. I only know the exact solution to the free one.
Okay, so we can take a break for lunch now. So just to remind you, I think you got an email, but the exam on Saturday will be in the morning, the same time as the exam on Sunday. So 9:30 it will start.